Hello and welcome back to another amazingly fantastic chapter on Gauss's law. Well, all this while we've been finding what is the electric field at a point due to a charge or a collection of charges, but you could look at the whole discussion in another way. What if we know the electric field pattern in a region, then what can we say about the charge distribution in the region? So, here is a box and we are not told if there is an electric charge inside it. What we know is that the material of the box is inert and has no effect on any electric field. Or to make things simpler, let us say that there is an imaginary surface in shape of a box that may or may not have a charge inside. And we will call this imaginary box as a closed surface, since you can see that it encloses a certain volume. So then the question for you is, can you tell if there is any charge inside the box, and if there is one, then how much is it including the sign of the charge? So to answer the question, one of the things you could do is to recognize the fact that if there is a charge inside the box, it will generate an electric field. And if you put a test charge, say Q0, around the box, you could measure the force at various points on Q0 and therefore the electric field at various points as E is equal to F upon Q0. So in a way, you could actually make a 3D map of the field around the box. So in this case, if you see the direction of the field map, you can clearly make out that there is a positive charge inside the box. And if you really get into the details of the field map, you can also find the value of the charge inside the enclosed surface. In fact, to determine what is the value and sign of the charge inside the box, all we need to measure is the value of E on the surface of the box. So in this box, there is one positive charge, while in this box, there are two positive charges. In each case, the pattern of the field is different, but the fields point out in outward direction only in both the cases. If we consider these boxes, seeing the pattern of the field, we can tell that the charge inside the boxes are negative since the field lines are pointing into the box. So that brings us to the concept of electric flux. And if we take the meaning of the word flux from Latin as flow, electric flux is nothing but electric flow. So as a convention, when the electric field vectors stick out of the surface, we say it is outward flux. And if they are penetrating the surface, we say it is inward flux. So it is therefore obvious that in case of outward flux, you will have a positive charge inside the box, and for inward flux, you have to have a negative charge. And if there is no charge inside the box, well, there is no flux simply because E is equal to 0. So if we have a negative and a positive charge of the same magnitude inside a box, the flux will be 0 since the net charge inside the box is 0. But you may note that there still is inward flux in one half side of the box and outward flux on the other side. The two set of electric fields therefore cancel each other, making the net flux 0. So let us take a step ahead and say that we have an empty box, but the charge is present outside the box. So what we have is a uniformly charged infinite sheet placed on this side of the box such that this face of the box is parallel to the sheet. Well, you can see that the electric field from the sheet that is uniform penetrates inwards on this side of the box and outwards on this side of the box. On other surfaces of the box, the field is parallel to them and neither penetrates nor comes out. So in a way, these sides have no contribution to flux in any way. So you see the inward flux from this side of the box is exactly cancelled by the outward flux from this side of the box, and we can say that since there is no net flux through the box, there must be no charge inside the box. So earlier we saw that for flux projecting out of the box, we take the positive sign, while for flux that is going into the box or the imaginary surface, we take a negative sign, or we take 0 if it is parallel to the box. Well, we could also show a connection between the magnitude of charge inside the box and the strength of electric flux through the surface. So you see a single positive charge of value Q has this as the strength of flux, while if we double the magnitude of charge, the length of the vector also doubles. So the takeaway is that doubling the value of charge will double the value of flux through a surface, or in other words, the flux through a surface is directly proportional to the value of charge enclosed by the surface. So now if you go ahead and say that the value of flux through this side of the box is product of the average E value through the face multiplied by the area of the face, then we could say flux is E times A square, where A square is the area of this face. Now let us double the size of the box so that each dimension also doubles. And we know that since the value of E falls as a square of the distance from the charge, the E value therefore should become E by 4 on this surface. But the area of this face for this box is now 2A square, which is equal to 4A square. Then the flux becomes equal to E by 4 into 4A square, which you see equals EA, which is the same as before for the smaller box. And if you do the same calculation for other side of the enlarged box, you know the result would be same as for the earlier box or the smaller box. So you see the size of the box has no effect on the magnitude of the flux. The increase in area through which flux is calculated is compensated by the decrease in the strength of the electric field due to the increased distance. So simply put, the flux due to a charge inside a box has no dependence on the size of the box or the imaginary surface, and depends only on the value of the charge inside the surface. So I repeat the 3 important takeaways from this lesson. Number 1 is the direction of the flux is determined by the sign of the charge inside the box or the imaginary surface. Number 2, if you have a charge outside the box, then there is no net flux attributable to the surface under consideration. The third point is that the net flux depends only on the magnitude of the charge enclosed by the surface and has no relation to the size of the surface being considered. So now the question you should ask is that do these statements apply to other surfaces as well that may not be as geometric as a box? Well, the answer is yes, and that is what we will explore in the next few lessons. So if you like this video, go ahead and give it a thumbs up, and please do not forget to subscribe to this channel for many more interesting videos.